I'm taming lightning. Percy got that lightning. Plasma in my veins.
Hello, Lightning Tamers. Percy here. There might be a few people coming in here over time, but we got some promo stuff to get through first. Welcome to the Taming Lightning Plasma Primer. This is the second live stream of January 2024. Let me switch over to my screen. So the whole point of this series is to basically do a whole bunch of different guidelines, but let me go through my spiel here on the presentation, and we'll kind of get into that. All right, so today's sponsor is FMS Sign Products. FMS has been providing quality products for neon sign industry since 1946 and strives to support dupenders by making it quick and easy to purchase the materials they need. FMS offers a wide variety of readily available and competitively priced products, which can be purchased directly through their easy to use website. Don't need a whole box of tubing for your project? No problem. FMS can ship partial boxes and mix and match colors and sizes as needed. Shipping is secure and easy anywhere in the nation. Check out their website, fmsneon.com, to see their full line of products and to see how easy it is to have all your neon supplies shipped directly to your door. Again, visit FMS Neon, that's FMSNEON.com, for all your neon needs, and use promo code LIGHTNING at checkout to save 10% off your first order. So, FMS mainly has been sponsoring the previous podcast, episode 56, which is the talk I had, a conversation on conservation with Susan Hargrove, who had just retired from her time as a head conservator at the Toledo Museum of Art. And then the upcoming podcast after this month, which is with Mark Ditzler, which will be with Adam Smo, they supported that as well. And I thought I would put them in between some of uh, these live streams just to kind of help get that out there. I know there's a lot of people that have listened to podcasts. There's some people supporting me through checking out the blog, but I want to get them out there because they are part of this network of partnerships that allow me to provide as many resources as I can to the community, both neon and plasma. So if you're interested in plasma, you may be thinking that maybe I'm not interested in grabbing neon products, but the thing is, you'll need your tubulation, which they sell in 6 millimeter. They have electrodes that I've been using in the process. I found that works very well for a lot of different glasses I've been using when I'm blowing glass. If you're looking for something like you're doing flame working, then FMS is not going to be your person. I do have a stock of borosilicate electrodes from the trade that's typically seen in Europe, especially in France. So you could check out taminglightning.net/store if you're interested in buying borosilicate electrodes. Sorry about that. I'm getting everything mixed up here. All right. So chapter notes is based off of the Intro to Plasma series that I did in collaboration with GEEX. So my co-host during that 4-part series, which you can find on GEEX, a YouTube channel, was with Ben Orozco. And what I'm doing with this series here, this short live stream, is I've since that collaboration, which was 2020 and 2021, I've been going back making guides to kind of pull some of the information out, especially things I thought were very important. We have a lot of people who are, working in glass, and that's sort of my target audience. But over time, sort of like, I believe what I'm putting together will give us a vocabulary that can meet between the artist, designer, and then the fabricator. So that's sort of the whole point of this series. And the plasma primer is sort of the little deal I did with Urban Glass, for the Urban Glass hotline. I don't know if they have that available for purchase on their website through membership, but I think it would have been awesome if I had that access, because then you could have seen the earlier version of this. But what I've been doing this month is stuff that I've been teaching in the last 2 years, using to supplement and teach with the classes I teach during the intensive, the summer classes and workshops, which are back to back, maybe from like 5 to 7 days to 2 weeks, with Pilchuck being the latest one I've done. So I'm gonna pull myself out of that real quick so you can see everything going on here. So in today's live stream, we'll be going over design theory and plasma sculpture. This is the first edition. I've sort of just been putting together a variety of different a variety of different sort of terms or attributes that we should think about. And the thing is, like, what I'm about to show you guys isn't like a fully comprehensive guide, right? It's a set of things I've observed and can support through imagery and experience. And so while it's not comprehensive, I think this lecture kind of helps fill the gap where some people may have some trouble understanding some of the information presented through um, just reading the slideshow. And I know some people have trouble reading, and so they learn a little bit better with someone speaking or talking versus reading, and things of that sort. So again, this is a guide that's supposed to introduce design considerations when creating your sculptures. And I'm going to kind of take a pause at different moments to kind of highlight where I just kind of threw these things in there, because in reality, when you come to something new, especially like plasma or neon, you already, as an artist, already have a sense of your design principles. It's just that when you are introduced to something new, you forget what you knew previously about design. And this is just kind of bringing your focus back again, so you start to think more closely to what your imagination wants you to create. So I'm going to move my head out of the way here real quick, and get back to the slides, because I want the slides to show up most predominantly during my lectures in this case, because there might be a lot of stuff on the screen. So a few attributes to keep in mind: discharge modes, electrode placement, visibility of cords or wires, level of interactivity, electrode type, and illumination. There's more after this. I'm just kind of putting some of the core ideas up front, and we're going to start off with illumination. So, illumination, aka lighting. Illumination is the light produced by the plasma, and it being not as bright as neon requires attention to lighting within the space. An example would be to dim the lighting or to use shadow boxes, as per the example I showed in my own work, Inspire Neon Citrus. This is our biggest enemy in terms of. I wouldn't let me pull back the antagonistic aspect. This is our one of our strongest uh, problems to solve, and it can be very difficult to be able to choose to correct and provide the most um, optimal environment for your illuminated works. Neon has that brightness, and so a normal gallery space is capable of 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 being all right for that setup. But when you have something like plasma, very indirect lighting, even lighting as like a very chill living room lighting, can make it very difficult to see the sort of details that happen within the light that's produced by the plasma. So being able to create a shadow box is a excellent way to kind of contain the piece. It also helps contain your electrical as well. which becomes part of the questions about how do you handle your cords and electrical wirings. Unfortunately, that's sort of up to you. We have an example here from Harriet Swartzrock Encircled, where she has a variety of these different hearts that are put into an arrangement, each of them having either a backdrop to help give contrast or shadow box to kind of protect it versus surrounding lighting. So this is more of her a style of arrangement, which can allow you to consolidate chords and whatnot. So again, you're curating the visibility and purpose of your lighting. And so, along with illumination, you're thinking about with your glass artworks, you're thinking about is how translucent, how opaque is the material? What are you hiding with your opacity? What are you revealing with your opacity? What are we seeing with your translucency? What's the focus here? Are we looking at sort of this shadow moving about? Are we looking at the direct visualization of that lighting and display? There's clarity and distortion. How are you treating the surface of that material? Is it nice and smooth, or is it bumpy? Does it have texture? Does it have lensing? What type of colored glass are you using? And how are you using that colored glass in conjunction with translucency and opacity? How important is the color that you're using? Because in our last presentation about the anatomy of plasma sculpture, in this section about gas mixture and color and phosphor, those things interact with each other. They will influence your decision making. If you have a color, you might want to think about how the lighting of the plasma itself will be directed based on the colored glass, or vice versa. Now, some of these things are a little more complex, but I've kind of put together the terminology for like discharge and discharge modes. And these are modes that describe the type of illumination seen in plasma that are primarily influenced. In this case, I'm kind of putting observation in place with this. This is again the type of illumination seen in plasma that is primarily influenced by pressure, gas mixture, and which geometry can affect formation. So we're starting to look at these different ways that light is produced with the plasma, but we're also looking at how things we can control. The volume of the space that's creating those objects, the way they were constricting things, and how much of those gases we're putting in there with the amount of power that we can illuminate the object. So we're gonna go through each different type, and we'll kind of see that we got a lot of overlap between. There's a possibility. There's not a super hard line for some of these modes, and these again are made through observations from looking at different works that people have made, works that I've filled, works that I've made, and having different discussions here. I think it was Chris Burak who kind of turned me on to these terminologies, so I really appreciate his suggestion quite a few years back. So a dark discharge mode is when the particles are ionized but aren't there isn't enough particles or there's not enough energy to produce light. And this is observed in very low pressure mixes as well as in non-illuminated areas of a vessel where the arc dominance is dominating the piece. And what I mean by this is that you have a lot of energy transferring and you start to see where the light is at, but there's that space that's dark in between. This could be, again, a measure of there's not enough power in the way that this whole thing's set up to illuminate entirely, or there's areas of pressure where it's not illuminating. And I'll kind of show a quick example on the next slide to kind of help us out. Actually, I thought I would, but that's something I'll add into my notes again because that's sort of how this works. Each iteration is I'm adding new stuff to it. So it does help to. How do I go back? I got so many screens up right now. So I think that's going to help us here with the glow discharge mode. At least let's dial back into the dark discharge mode where there's no glow. If you look here on the screen where I'm pointing on Harriet's piece, there's a piece of glass here that's not illuminated, and that non-illuminated area will be an example, I guess, of a dark discharge where there's enough ionization happening there, but once you touch that corner of that tendril, the light will illuminate through that piece. So, what is a glow discharge mode? It's pretty straightforward. It's when the ionized particles giving off a glowing appearance with light filling the internal volume of the vessel, similar to the glow of a neon tube. And to kind of give you some sort of numerical perspective, this is observed in low pressure ranges, approximately between 1 to 100 torr range. And this, again, will vary depending on the gas or gases used, the scale of the object, and the geometry of the vessel. There are moments where you would think, well, it shouldn't produce a light, but you used krypton or you used xenon. And those are known to form a filament or line of light much more easily and much more likely at a lower pressure. And we do have examples for this in the next slide. So you have works by Angela McHale, episode 55, and we have a geometric cluster, which is a study that he was doing trying to think about how he would use plasma by John Sharvin. And we can see that predominantly we're getting a glow. We're seeing that the light is filling the internal volume of the piece. There's no dark spots, there's no overpowering line. You're going to see an arc within shots fired by Angie, but it's not predominantly the purpose of that. It is based on the geometry compressing that space. And we even see an arcing or a sort of a beam of light coming here from the electrode, and that again is moving towards a constricted point. So then we have the arc discharge. An arc is described as a luminous electrical discharge between two electrodes or other points. Excuse me, I have a bit of a cough here. So this is the thing that people really love about plasma. They want to see different effects. They want to see different colors. They want to see different like behaviors. And the arc discharge mode is when the ionized particles follow a path of least resistance, and that forms an arc or arc of light or a filament, such as lines or threads of energy. And they're not always linear, and they can form unusual shapes. So that's why I'm not giving a strong definition to what you're going to see, because when you see more examples, there's not a way you can describe that whole range of unknown possibilities. Now, when you're trying to observe this in pressure ranges and gas mixtures, you're observing this in a higher pressure range. Again, this is approximately 100 torr of atmosphere, 100 torr to atmosphere, atmosphere being 760 torr range, and it varies based on the gas or gases used, scale, and geometry of the vessel. Again, I emphasize again how the shape of the glass and how much space you're giving the gas can influence the way that the gases that you use are playing out when they're excited. And again, we have more work from Harriet Swartzrock. She's done so many pieces that I can throw out an example of a lot of different effects just from her catalog and documentation. So we're seeing this fine line of light, but we're seeing these little sprites dancing off on the edges as you touch the piece. And that's super exciting. So we have some more examples of arc discharge modes. And I thought I would use Ed Kirshner's work as a great way to describe this because he set up certain conditions with the way he's lighting the piece and where he's directing the light to create different displays and behaviors in the mixture. And so the plasma woods has a line of positive and negative strips, grounding and high voltage to create these different effects. And with the same thing with the dancing daisies, there's a plate that's drawing the energy towards the top side of the cylinder. And that gives us with the gas mixture, gives us a particular display of light dancing and moving and joining and separating. So you have people like Harry, who is a mixture between form and light. And we have someone like Ed Kirshner, who is focused on creating very simple geometries and then creating very dynamic lights through gas mixture and direction of energy alone. And when I say direction of energy, it sounds woo-woo, but what I mean is that the way a plasma globe works is it sends out a radio field of energy and it lights up the gases. It's when you touch the glass that you ground it that it starts to draw itself towards your hands. But if you do this in a way that draws energy from the high voltage wire from the bottom plate to the top, or left to right, or diagonally, or you choose multiple parts to draw energy towards or away from, then you can create different behaviors and effects within the plasma itself. You can direct the energy. And if you can direct the energy, you can direct the light. So we have to think about these types of works. As I mentioned, you touch it, it starts to glow or draw itself towards the surface being touched. Even the behavior of not touching the glass work by being in proximity is also a possibility. So we have to think about the levels of interactivity. Most galleries will not allow for touching of the artworks, and this is mainly for the liability reasons. Talk to Angie, she's talked about people allowing people to touch some of her work, and then had ended up finding that it got broken or something like that. So when even if you are set up to say how the work be touched or not be touched, regardless of whether those decisions are made, plan to make your design and build it on the level and safety of museum displays. And I kind of threw an extra slide in here that's coming up next to kind of give us an example of one idea that I think about for that. But again, you have to plan for people to be incidental in their behaviors. You could tell people up and down. You could put all the signs out there, which you should. But people will do things they're not supposed to. And if you want to protect your piece and to protect your patrons and viewers, do your best to put up the signs, and then do your best to put up the structure that prevents the pieces from being moved or broken or falling. So one of the ways I've sort of done this is I've changed from using the typical French cleat, which could, if you think about it, this thing can move left and right if someone pushes it. So if I have a framed piece on the wall and it can be pushed left and right, there's a chance that someone is a little reckless with their strength could knock it off the wall. But if I use something that's more kind of a finger that locks into place, then it can't move left or right. And someone would have to physically lift it up and off the wall in order for it to fall off. And that's a little idea of why, like, a change you could do to prevent and keep your structure strong versus an incidental interaction. So we have talked about the different displays of different types of light produced by plasma. We talk about the potential uh, interaction of the artwork. We talked about illumination, and those are things that you can start to develop um, as you work through your artwork and your basis. But the thing that's going to really pull this stuff together is typically about your electrode and where you place it. So your electrode placement is the origin of your illumination and will often be the brighter spot in many of the plasma pieces. And we have two examples here where we have Fumi Amano, who has done some work, and and I have to say this: I say to resist the urge to settle for what is convenient and be intentional to where you place your electrode. If you want something to look really nice and you want something that you don't have to like create a whole way to hide where the electrode is, then you have to be intentional about the placement. It has to make a lot of sense that we ignore that there's a electrical thing on there. You know how you have a lamp and you can ignore that it has a socket and a light bulb in it. You want to ignore that part of the object. Um, so this is something you have to really think about when you're making the work. If you're just playing around with trying to get shapes done and you're just trying to throw it on there just to see what's happening, no problem. I have no problem with that. It's when you're coming to me after having done that and you want that to be your final piece and you don't like that you have 3 inches of electrode sticking off. But that I digress. The matter here is that Fumi has made a really great intentionality in the placement of electrode, being the opening of the vagina here on the female reproductive system, and we have the umbilical cord on the sort of fetus or infant character. So these make a lot of sense visually that I know as a plasma person where the electrode's at, but if I was just glancing at it, I would not even pay attention. I'd pay attention to something that's being illuminated. There's a change in focus in the art piece. Some other examples of electrode replacement, they're very simple. You don't have to do some crazy thing to hide it. If it's integrated and it's protected, you ignore it because you shifted the focus away from that electrode, such as in Wayne Strabon's piece, where it's just embedded inside of this little holder, and it's part of the hanging mechanism on Patrick Collentine and Susan Larson's piece. And the next slide will give us a close up, seeing, you know, these are perfectly fine examples. They don't seem out of the sort. And I think it's because these works are linear. And if you start to make more volumetric and sculptural pieces, the electrode becomes a protrusion. So think about that. In the same way, I've made my adjustments in my own artwork. Notice the difference between these pieces. You have 3 inches sticking off the bottom of the piece where the electrode is attached, and then I've decided I would cut down the shell and embed more of the electrode into the body of the object, creating less of a protrusion in the piece. And sure, the electrode shell, the metal can that's sitting inside here, becomes another focal point, but I've reduced to sort of leverage this arm sticking outside the ride situation where, believe me, I've broken pieces I finished just because I had 3 inches of electrode sticking off. And that could be heartbreaking, especially if you really like the piece. So finding ways to remove and embed and remove the protrusion of the object that doesn't factor into the sculpture at all, besides being um a practical means of getting electricity from the outside into the glass, is one of the ways that you can start to protect the piece and do a little bit better with the way that you build your artwork. So now we can start talking about electrode types. This section here is, again, this section here is observation and categorization. These aren't things you'll like go in a book and say, oh, this is a direct type 1, this is direct type 2, this is what this is called, this is what that's called. Because there's so many ways you can put an electrode onto a piece, and there's so many ways that you can create sort of this connection between the transformer providing electricity and the connection to the gas inside to be excited. I thought I would observe a variety of different works and kind of provide a scope of ideas. And that's what I'm doing when I talk about direct and type. And I'm doing three things here. I'm giving you some sort of a name. I'm giving you physicality. Is it direct or indirect? And I give you a type to tell you there's a variation. And this just sort of will help us kind of understand and observe how other people are handling problems and how we can expand and find new solutions. So the neon electrode and its variants, which is direct type 1, and how I describe it here, because I try to put a definition so you can understand what I'm talking about when I name these. So direct type 1 is the use of glass to metal seal to attach a metal that has direct contact with the gases, such as the standard neon electrode, which are abundantly found, or that which is made by hand as seen in Geisler tubes and scientific apparatuses. The neon electrodes were designed to focus the light directionally in the tubing. But for but as we discover in plasma light sculpture, the discharge, the electrical arc, will leap from the least resistive part of the electrode, which doesn't always mean straight down the tube. And on the left, we have three different types of electrodes that are of this direct type 1. It is within a single cylinder of glass, and it has a through metal seal of wire and something to direct that beam as a canister or a rod inside the cylinder. So we have borosilicate neon, we have our soft glass neon electrodes from various companies, and then we have something that's handmade, such as the one made by Bruce Suba using tungsten. And the material is of tungsten is often used in scientific work as well. So the tungsten boro neon electrode is something that one could make if they had the right materials and the skills to do so. Again, reviewing the types, the pieces that use sort of this direct type 1 neon electrode. The other one, which I would categorize as a wire or filament in its variance, is direct type 2. Direct type 2 is similar to direct type 1, meaning that instead of a short cylinder or rod, it's a long wire or filament like configuration. The wire or filament as an electrode provides a surface for the glow to form around or for an arc to jump off of, allowing the light to travel the length of the wire. And we have some examples here. So there's Gestural Piece by Mundy Hepburn and some student work by Clyde Jurista. Part of the reason why Mundy would use this wire to follow through the whole body of his long pieces, these pieces can be from 5 to 6 feet long, is to help direct that energy down through the piece. Sometimes, if you're going from a single high voltage, which is what plasma is predominantly doing, it requires so much more energy to keep pushing electricity down through the piece. And if you have such a long and voluminous piece, cranking up the power may not be the best solution because it also has other things that happen. But you can get a very beautiful effect with the wire, which also assists in drawing energy down throughout the body of the object. And that's what we're seeing here with Mundy's piece on the left. On the right-hand side, we have a student who's thinking something unique. They're like, well, what if I wired up using some steel wire and made some sort of cage or some weaved objects? I'm like, cool, do it. Because that was something I was thinking about. And then they did it, and they mechanically bonded that wire to the electrode, and we have this effect. If you look and observe it long enough, you start to see there's sort of a dead zone on the inside. All the energy from the plasma is expressing itself outward from the cage surface and not just staying on the and not floating in the inside or crossing the inside area. It's reaching out, it's moving outward from the center point. Very great stuff. And I want to throw in an additional example because sort of this aspect kind of reminds me of the Aurolux light bulbs, which these are like copper or metal or little figures made inside the bulb that are then coated with phosphorescent powders. So when they light up, you get different colors being expressed. So you could build all sorts of metal structures. It doesn't have to be glass; it could be metal structures that illuminate or glow. And this is more of like a glowing effect. You could still probably find a few of these ideas for Aurolux in the store. You might see like a flower or a name like Love You or something like that, whatever. But some more vintage stuff is a little more decorative and more expressed. So um, that's something also to look for, and research and kind of be inspired by. This is something I just added recently. And then we have our third type, which is capacitive coupling or indirect one. Um, the indirect type 1 is the classic plasma glow. If you're not familiar with how plasma glows are designed or work, don't worry, I didn't know myself until like a few years ago. And basically, this is where there's no direct contact between the transformer and the wire and the gas. Instead, it's using conductive material as an interface within a cavity or a pouch designed in the vessel. So there's like a little stick or rod inside of a globe, or in this case, a little pouch or pocket, that then something conductive like stainless steel or bronze wool is then expressed with the high voltage, and the high frequency expresses itself through the walls of the glass, exciting the gases. This electrode type, which can also be considered electrodeless, has the advantage of using non-inert gases and halogens, as there's no metal components for the gases to react with. That's the biggest advantage here, is that you don't have any metal that you haven't properly processed. If you have the glass nice and properly baked out and heated up prior to filling with your gases, you could do a lot of crazy new things. But it then still presents a issue of how are you going to properly provide that surface to provide that frequency, to be that radio frequency antenna for the high voltage and high frequency wire. And I know this sounds like gibberish, but like, it's better if I just keep showing examples because then you start to understand. So on our far right, we have an example of the classic plasma globe. It's a sphere, it has a little rod, a tube in there. It's coated with some conductive paint, and then there's a steel wool stuffed up there, and a wire goes from the transformer to that steel wool, and it expresses itself outwardly. That's how a plasma globe works with the capacitive coupling or indirect type 1. And if we look at an example from Wayne Strabman, he has this tube piece, but there's a tubular structure on the inside, and he's using, and I think you won't mind if I tell you guys this, he's using mirrorized solution on the inside as a conductive surface. And then he has his high voltage wire go up to that with maybe a little steel wool stuffed in the bottom, and that charge runs along the surface, interior surface of that tube, and it expresses outward. And by choosing to use iodine and some other gases and getting to the right pressure, he has this unique expression around the areas that are closest to the side walls, which is very neat. And that's his piece. That's Wayne Strabman's piece, Metropolis. I've also done similar experiments. I would kind of consider this next piece like an indirect type 2. It's similar, and I differentiate it because instead of using a pouch, I'm using part of the surface. And in this way, I created a connection point that was both the mounting hardware and the surface that the high voltage would be expressed through. And I use this as an example to bring up why it's important to really plan out your artwork, to really understand what you're doing. Because when I did this collaboration with Chris A. Halt, and I know he doesn't mind if I say this, I've said this before in a video, we just like wanted to work together. And this is 2017. I didn't know anything, and I know just a tiny bit more today. But he made this beautiful moose head piece, but we didn't design how the electrode would be put on there. We decided not to have an electrode. And then I just had to figure out how to mount this thing and make it look good. And it took me until 2020 when I bought a 3D printer to figure that out. And the help of other people, like I found out about the conductive silver conductive epoxy. Um, I learned about Aquadog E, the conductive carbon paint from the late Gavin Tiernan. And then Aaron Rostall suggested using Sugru, which is moldable silicone. So you put all the things together. I first sandblast the back of the piece to give it a bit of a tooth, and then I would paint on a little bit of the carbon paint. And what that does is it creates a surface that the electrical charge can travel across instead of just being a hot spot where it starts to focus energy, because that's what we don't want. You want the surface to distribute the energy, not create a hot spot where it could heat up the glass or crack or punch through the sidewall of the glass. I then use the silver conductive epoxy to adhere the wire to the back of the conductive paint. That I molded the Sugru, the moldable silicone, around the piece to insulate it so there's no air gaps. And then lastly, I forgot to mention here, Harriet introduced PC7 epoxy to me, which allowed me to bound the mounting hardware that was 3D printed to the back of the glass. And you can see the results are similar, and this piece now lives with Chris Halt and his family. And when I was able to really find that solution and get things sorted out, I was very happy to be able to send that to him. But again, that took me 3 years to think of a solution, and it probably could have been faster if I had planned things out a bit better. But it's a lesson I could share with you guys about planning and understanding what your end result is, and not just get too excited about making something cool. That sometimes you slow down to actually sit down and think about your steps, so you don't sort of put undue amount of pressure on yourself or disappoint others. And then we have some other examples. Again, Ed Kirshner is an example here of, again, indirect type 2, where he's using a flat glass panel on the back to produce the high voltage, and then grounding the top side so that it draws energy to the top surface of the cylinder. So using conductive sheet glass and electrical wire on both the ground and the high voltage of the transformer to give us a specialized effect. And he's dialing in his gas mixture to get something that he really likes. So I guess if I were to rewrite the definition here, indirect type 2 is just using other non-conventional aspects of the capacitive coupling to get different effects. We have another piece by Ed Kirshner, an experimental piece, where he's creating this helix effect by wrapping a wire around the outside. This is an insulated wire wrapped around the outside of the tube, and then one of it has high voltage, and the other side has the ground, so they're crossing each other within the glass tube, and that creates sort of this helix effect of the electricity traveling along the wire. So there we go. We got 3 types. And I'll kind of go back through that real quick so we kind of let our brains reset a little bit. So you have direct type 1, which is using a neon electrode. It directly interfaces with the glass piece. You have direct type 2, which is using some kind of wire or filament or construction inside the glass made of some kind of metal, which functions very similarly to direct type 1. You have capacitive coupling, which is indirect. There's no electrode. You're creating some kind of pocket or internal tube or cavity and using some type of interface to direct the energy along the internal surface to project outward into the object. And then indirect type 2 is using the surface in unique ways. It's either part of a surface that's circular or drawn out. It could be 2 flat glass, it could be conductive panels drawing against each other. It could be wires moving along the surface. One of the first things that people come to me with questions about is usually about gases and how to put on the electrode. And this is more of a directed towards soft glass workers, whether they're fused glass, kiln glass, cast glass, or blown glass. Because the idea here is that, and I'll read directly from my thing here, because the idea of attaching method is directed towards soft glass. And this is directed towards that group because, for the most part, and the way we navigate art glass, the scientific and methodical practices of flamework glass have already understood how to meld it together into a sort of this seamless connection. And not everyone knows this because it's sort of part of an idea of holding gas is different than holding liquids, but the practice is all the same here. So, as a soft glass person, we want to find ways which we can observe other practices and apply those to our blown glass process at the furnace, or apply methods that allow us to fuse things together in casting or fusing. And in the hot shop, we can think about our observations of the technique called encolmo, which is an intensive focus of heat on the lip of the 2 cups before joining them together. That essentially they become one piece of glass at the connection point. That intentionality is what you want to apply if you're going to do some sort of sculpture in glass at the furnace in which you're adding multiple parts and cavities and sections. Additionally, knowledge of sealing materials that are absent, such as using glass solder, can help you out in the same aspect. So knowledge of sealing materials are absent in a natural transition to making a better vacuum sealable vessel. And what I mean by that, and I know it's kind of confusing here because I'm trying to add stuff to it as I talk, but the idea of making a smooth transition in your connections in hot glass will make everything that much better. And you'll hear from flame workers and scientific glass saying we get away with a lot of stuff when we are working in the furnace glass. We are doing connections, we're adding bits from surface temperatures that are vastly different and much cold comparatively the way that we want to attach borosilicate or you want to attach frit to our cast pieces. And, you know, not to harp on furnace blown glass, but these forms of art glass in the art glass realm have nearly not needed to resist the influence of vacuum or atmospheric pressure. Much of what we do in this artwork hasn't required us to contain gases. So again, it's an important note that sampling and understanding other knowledge, cultures, and methods broadens your application of technique and sharpens your artistic practice. So let's really look at some of these ways that we applied electrodes in a soft glass context when it comes to furnace glass blowing. So one of the methods is to tubulate and weld, or tubulate and seal, because some people don't like me saying weld because it seems crude. But I think we should broaden what that is, and both weld and seal to me are comparative. You have to make a good weld, and you have to make a good seal, and both can be really beautiful and well made. So the idea of this tubulate and weld is you're pulling a tube off the body of the vessel. You're pulling off a section so that after it has annealed and is at room temperature, you can weld on an electrode with a hand torch. And this is something that Harry has been getting really good at doing. She creates these heart pieces. They have these little tendrils and tubes sticking off. And then she spends time welding on those electrodes very slowly. And if you think about some things like, what are the advantages of this thing? Well, the advantage here is that it's comfortable for you. You don't have to think about this ticking time bomb of this glass cooling too quickly and going to crack. You can position yourself to weld in a very comfortable and stable manner. And you have a lot of time that you could put into heating and then getting the electrode attached. The disadvantage, or rather the creative requirement of this process, is that the protruding tube would need to be considered in your design and your display of your artwork. And then additionally, this adds another step to re-anneal that glass. There's people that can really, in the scientific world, could really flame anneal glass work. But the thing is, soft glass doesn't give you that much more of an advantage there. You could be the best and still have that thing crack. Especially if you look at this piece, it's very thick comparatively between the glass and the electrode, and that difference in thickness, regardless of your transition, means that some part of that glass is very stressed out. So it's very important that you go ahead and you re-anneal that piece, but build that into your practice. Don't shortcut nothing. When you try to get away with something, it's going to catch up to you. But then we have the other method, which is direct weld or direct sealing. In this method, you attach your electrode using a blowhose by heating both the opening of the vessel that you created through your sculpting and the electrode end with a torch. And then you stick those two surfaces together and then blow, creating a nice even transition of glass. I think I might have some video from students from this past workshop at Pilchuck that could give you a better visual of that. But if you go to the website about electrode attachment, I do have another video I did myself that could give you some context to that. So after you stick the electrode on and you blow to create a nice even sloping transition, um, you have the choice of doing this either while the piece is still on the punty, which means it's your last heat before it has to be knocked off and put away, or it is done as knocked off onto a knockoff table and you spend the time heating, attaching, and have someone running that piece over to the annealer. Now, the reason why you would have to do this on your final heat is you want as much heat in there as possible, that you can have as much time as possible to add the electrode, and it's still being above that 1,000-degree temperature. Now, the advantage of this process here, or this method, is that it's simple, and it's a very direct way to do it. And the glass will anneal with the vessel. But the disadvantage, and again, creative requirement, is that you have this protruding electrode that you need to consider in your design or display of your artwork. And then there's definitely a risk of breaking the electrode by heat or by handling. So the problem here is that the person that you're having put this away in the kiln, you have to trust them to put it away properly, and you have to trust everyone else using that same area not to throw their artwork against your piece or bump it. And then you have to trust the people at the studio who may be in charge of removing pieces and setting them aside to then not break the pieces when putting them on the shelf. This is why this is a sort of a very problematic. If you are renting out a needler yourself, then you can come back the next day to unload it yourself. But you have to be on top of your timing to make sure you're not impacting the studio. Remember, a public studio is for everyone. So whatever you're going to do, you have to be able to play nicely with everyone else who's going to use that same space. And that's why, even though this is a very direct way of doing it, and a lot of students can start to understand what I mean by creating a nice smooth transition by practicing this way, um, it's probably what I would least do nowadays. I prefer the next method, which is using a kiln fired glass as a solder. And so this idea of a glass solder is nothing new. There are many types of solders used in vacuum sealing that are commercially available, but they can be expensive and not generally available for the consumer, right? So what I've done is I've learned from Ed, who tried out different types of glass enamels, tried them on different types of glass, tried them on different types of compositions, and he found that if you can use the Rouchet soft flux, it can make a binding. It can be used as a glass solder, joining two different surfaces by melting the enamel itself and not having to slump the other pieces of glass. So again, by kiln firing a low temperature enamel, you can fuse the glass components together without them slumping. And that's how I could kind of embed my electrode in there. And sure, things are going to be sloppy when you start out this stuff, but as you get better, you start to be able to find the right mixture, the right amount, and you get a much better and cleaner mixture. So let me talk to you about the advantages of this thing. Well, this allows you to break up your process. It allows the creation of a unique glass vessel in the absence of or the accessibility to glass blowing skill. Which means people like Ed Kirshner, who relies on other people to make some of his glass artwork, can still make his plasma vessels by buying ready-made glass and stacking and creating different forms. But this also allows you to explore glass making process in the likes of fused or slump glass, like Mark Ditzler and Wayne Stratman's lumen glass, and even start doing stuff with cast glass techniques for plasma illumination. Additional advantage here is it reduces the protrusion of the electrode in order to better integrate with nonlinear vessels or explore more complicated vessels of the furnace glass blowing. What I mean by this is that I split by process, and when I'm working in the hot shop to make my vessel, my glass sculpture, my hollow form, I can focus just on the hollow form, just on that. I can do more complicated things, and then as long as I plan where my electrode is going to be through the way I manipulate that sculpture, I can then separate that part of the process of adding the electrode into a more controlled and decisive manner. That's why I like this method. Now, this protrusion thing, does it work for flat glass vessels? Not really. You still have to, you can't really compress that cylinder into the piece. But maybe someone's going to design something by hand that makes that electrode shorter and less protrusive. And that'd be great. But then there's some disadvantages here. Or again, I want to call my disadvantages creative requirements. It is a time consuming part of the process, as it takes one or more firings to sometimes get a successful seal. Which means you can spend maybe 2 to 4 days, depending on your thickness of the glass, firing a piece just to get that electrode to seal on properly. There's a risk of breaking the glass vessel if your firing or annealing cycle are not well developed. If you don't have that down, your firing the scheduling log for your annealing cycle is improper, you can lose a piece that you put a lot of work in. And I've done that. But the reason why those happen, mainly because not really inexperience, mainly because I was rushing the process. Don't rush the process. And then lastly, this process is only really effective in vertical assembly. That means in line with gravity. So securing pieces with kiln furniture is like you're basically building up your infrastructure when you're getting these pieces set up. Now, the piece I'm showing you right now, I didn't have a lot of. I showed sort of this little standoff here. I would have a little piece of kiln shelf sliding here, another piece of kiln furniture sliding here to kind of center and cross section the electrode. After it's been fired once, it's fine. But then I learned later on I didn't have to do all that really, as long as I have some sort of tooth or surface. So, depending on how you're making and what you're doing to that surface, you may have to do some a lot of propping and supporting. But when people ask me, well, Percy, why would you do something like this? And I will show you guys next week with going through the process of making this piece. Pretty much, I find it no different than anyone else completing any part of artwork. You still have someone who has to put a lot of time into making a whole bunch of vessels, regardless of whether they have the coal work or not. You have a lot of people having to do that with casting or coal working pieces or flame working pieces. To me, time's not even an issue no more. It's do you want to do the process and do you enjoy the results of your process? Visibility of cords and wires. So we have to acknowledge that this thing requires electricity, which means there may be a need for cords or wires, and that sometimes you have to connect that power supply to your piece. So not only do you have to have a power source going to your transformer, you have to have your transformer connecting to your piece somehow. Most likely, you're going to have to use some sort of wall power, which means an outlet, and that means cords are involved. So cords and wires are necessary, and you have to make some creative decision making to support that. And ideally, there are four choices here of handling wires and cords. You can hide, minimize, ignore, or integrate. So you could ignore the cords by minimizing its visual impact or having cords that match the wall color. And I'm just showing you a quick example of my work that I put in that I had in a show called Aspire 2. So Inspire Neon is in the black box, and then you see that cord, just a single cord coming down to the outlet. You can see the cord, but it's not crazy, it's not messy. It stands out because it's black, but it's not drawing any extra attention. The attention will likely be on the piece on the wall. Then you have the Atupa Limelight, where the cord is white and it just comes down against the wall. It's virtually ignored. Now I thought about, okay, Percy, what if we had like a battery pack? Well, that comes to the aspect of making sure that you can, well, can you charge it easily? And do you need to take the piece off the wall or move it from the pedestal to charge? That has to be part of your build and assembly of that object. So that's another question you have to start asking yourself. You could minimize cords or wires if you could find a way to charge it, know the runtime of it, and then again you have to have someone maintain that. You have to have someone charge that piece every once in a while. So when it comes to galleries, you want to make it so that they're not feeling like they have to do extra work just to show your artwork, unless they really want to. But I tell you, most likely they don't want to. You could ignore the chords and have the artwork take center stage. And this could get messy in larger installations. And this is work by Harriet Swartzrock. I'm not being mean here. I'm not being mean here when I talk about this. I just wanted to show you examples of people who presented work, and that sometimes it sometimes it just works. It can work. But you can see there's so many pieces here, and if you don't have control of that space, then you kind of can't do that. And I can understand why she would leave it alone because you never know where power access is in a studio. I mean, in a gallery, I should say, in a gallery. And that sort of is the problem with chords, is that if the art gallery is not used to and not designed to show electronic work, then it's not going to have outlets in convenient spaces and convenience places. But then we have redemption here. But that, again, you can hide the chords behind the wall or in the base, or in this case, through the building of a false wall or false gallery wall. And this is part of the installation spaces between stillness and movement that Harriet has done. And it's amazing. You should see the video on her website of what they had to do to build this wall, but you can see just the difference between that sort of access. But when you watch that video, a ton of work put into designing this false wall to make the heart stand out and not distract with the cords or wires. It took a lot of time, muscle, energy, and money to make that happen. But we're not done yet. We still have to go through the last thing, which is geometry, and then we have to go through some examples. I know it's a lot. I have a lot of students who I've done this lecture with, and it fries your brain a little bit. But being that I'm recording this, you can go back through and take it at your own pace. So geometry relates to your scale, open and constricted areas, figuration, and abstraction. So it relates to shape or form of a surface or a solid, right? And so scale and volume, which are only limited by, which in the case of glassmaking is limited by the capabilities and limitations of the artist and maker, their facilities, and the technology we'll be implementing, such as the commercially available single end transformers. You can only make this piece as big as as your team can manage it, as big as the furnace allows you to get as much glass, as big as the annealer you have to put it in to cool down. And then you can only make it as big as the technology you have to power it. And you can only make it as big as the available gases you have in your manifold system. So this is why sort of scale, people want to make big things, and I tell them we should dial it down a little bit until we can figure out a few more things. And this doesn't stop people like Mundy Hepburn. You've seen some examples of his work. Definitely check it out. Listen to him on the podcast. And he builds monstrous, big, voluminous things. Same with Wayne. And each of them have such a stock house of different transformers, or Mundy makes his own, or they have particular mixes they use that are effective with the tools that they have. But they have the resources to make that happen. The thing is here, the larger scale, the more volume you have, which allows you to have more room for the complexity of your gas mixtures. So once a vessel becomes larger than the volume of a basketball, we start to get into challenging territory of having enough power in your single end transformer. So I wanted to use something that was as universal as possible, which is using sport balls to kind of illustrate scale. And most of the time when we're doing a workshop, you don't have a lot of time to make humongous pieces. But I say the biggest pieces we'll make will probably be about the volume or scale of a football. In that case, anything less than that, like less than the basketball, less than the football, say a baseball, a tennis ball, a softball, it becomes challenging to get a lot of different effects. So you're sort of limited to a smaller palette of arc discharges, or a smaller, or limited to just a glow discharge with interesting uses of your texture or the sculpture that you're sculpting. Open and constricted. This is the modulation between narrow and open spaces, and that's going to affect the arc of light that can behave in your vessel. How the arc of light behaves in your vessel. So this is just an arbitrary image to kind of show you, but it illustrates pretty well in a glow discharge, where the constriction here compresses the light into a brighter section of the piece. So plasma will be concentrated within the constricted areas, and generate arc formations. So you have to be intentional and not incidental in how you form your constrictions. And I don't think Sharvin would mind so much, but we've done a couple pieces working together where we joined two separate little geometric pieces, and the connection point was so hot it was just kind of mushed together. We created more of like a pinpoint hole between the two sections. And what happened is, even though we could evacuate those pieces, meaning remove air by using a vacuum pump, when we wanted to have a special effect go through between the two chambers, it wasn't going to happen. And that constriction, which was incidental and not intentional, made it so that piece didn't make the cut. Again, these overly constricted areas would create bottlenecks in the evacuation process, meaning it may take longer or it may not be as clean without taking more time. So it's always really important when you're thinking about constriction areas and open areas is to remember you are sculpting both the external surface as well as the internal volumes. Both the inside and the outside matter. As artists, we have a variety of things we can make. Figuration and abstraction are something you want to keep in mind. The two questions I may ask you here is, do you want the light to take the center stage of your artwork? Do you want to incorporate light in a greater narrative? The idea here is that you're going to find a balance in the surface and the form of your light that you like to display inside your plasma illumination. And this little slider, this spectrum, if I were to say, between figuration and abstraction, is not absolute. It's just an idea that if you have more of a detailed figure that you're creating, then you may want to have a simpler plasma effect, meaning more of a glow, less sporadic. But if you have more of an abstract, or think about abstract as simpler or shape, then you can be more dynamic because then you can let the dynamism of the light fill the shape. That means if you have so many details and textures on the surface and you have a whole bunch of crazy light, then you really don't know where to focus. You really are doing yourself a disservice. Say if you were someone like, at that skill level of, Marianecki or um, Grant Garmezi, where they spent a lot of time putting in texture. And then if you were to light one of those pieces with a crazy dynamic light, then you're kind of pushing out the the attention away from the details they painstakingly put into that object. That's just an idea that helps you kind of think about how you want to manage your artwork. If you're going to make it super detailed, you may want to have less of a dynamic light. If things are a little bit simpler, more abstract, and more voluminous and more blobular, if there's a description, you could be more dynamic. And we'll go through some examples. I think that might help us out. So this is the cool part that I'm really proud to be able to put together, and this is geometry through similar gas fields. So I've collected a few examples of all of which have neon and are an example of a glow discharge mode. And sort of as I go through the next few slides, I'll kind of ask questions to help guide your observation. And this will help enhance our prediction for how the plasma navigates various shapes. If you think of any new questions or have any your own observations outside the prompts, feel free to email, feel free to comment, feel free to post about it. So let's look at some geometry and how it can affect the plasma. So using geometric cluster, a study from John Sharvin, what's happening at the edges where the two planes meet? Well, we're starting to see, if we start to think about it, we're seeing a brighter red-orange glowing at the corners. We're seeing hot spots, bright lights at the vertices, the points. What do you see at the constriction between the two geometric shapes? We're seeing a brighter white light. We're seeing a formation of an arc. What options does the form allow for plasma? We chose to do a glow discharge, but this thing could have easily been sort of more of an arc discharge piece. It could have been more expressed with various gases too. But I still think that this is still a great choice for this piece to have a low glow discharge of red, orange, neon. And then note the location of the electrodes. Does it make any sense? Sure, the connection was more arbitrary, but I think because of the scale of this, it can be hidden behind some kind of armature. As a study, the electrode attachment point does not matter as much, but now that you see this and if you do like it, now you have to think more intentional about how you want to add that electrode now. And we'll look at the Plasma Moose Trophy from 2020, collaboration, Blown Glass by Chris A. Holt. This is also just neon. This is bluish, like a light blue, transparent glass. What does the simplicity of the plasma allow for the figuration? It's not distracting us from the details that Chris has masterfully put into his artwork. What do you see at the constriction of the antlers? You're seeing that the flattening of those antlers, curved, and the points create these little areas that the plasma wants to arc and point into. It's compressing the gases, it's compressing the light. How does that differ from the face of the moose? The moose has a little bit of an arc going along the muzzle there, but it is mostly a glowing effect. What type of electrode is used here? Well, if you pay attention to the slides here, we know this is a capacitively coupled electrode, and it's sitting on the back side of the moose's head. And does the location of the electrode make sense, and why? So then our next one here is the Chalice of Chaos. I want to say this is predominantly neon, and I'm pretty confident it is. There may be a little bit of krypton in there, but I've seen this sort of effect happen without using krypton, so I'm very strongly believe, and I think if I were to reach out to Ed, he would say it was just neon. And we have two examples. We have the cup of chaos, a chalice of chaos, and the vase with a cup of chaos. So what do we see at the constriction of the bowl and stem? We see at the constriction of the bowl and the stem this bright line of light. It's forming sort of this soft, very soft arc. What type of electrode is used here? Well, we can't really tell here with the vase, but we could tell, I think, with the chalice, um, this might be with an electrode, and I can tell you from the vase with the cup of chaos is likely to be an electrode attached on there in the bottom. And does the electrode make sense and why? Is this vessel a drinking vessel? No, this one's not a drinking vessel. It has you can't see it here, but it has a strong base there, and same here. Though if I were to add maybe some examples from Taffy, you'll see that he's made works that are meant to be picked up and drunk and used. Amazing cups that are meant to be drunk and used. Um, and I didn't add a question here about looking at the bowl, but we see that bowl shape. Particularly, Ed's very particular about the way that the inside of that bowl meets for the lip. It allows it to create a geometric pattern when compressed. So you have this long compressed surface that's created a geometric pattern that's not too dissimilar to the way that some sort of patterning is being affected in the Moose Trophy. So taking that these are all still the same low pressure neon, we're still getting that glow discharge. Sorry about that. We're still getting that glow discharge around the ring here, wherever there's a section where energy can go to a point, we see a brighter section. We see a compressed area. We see a pattern. And we look at Harriet's Untitled Heart piece here, the red one, which I have one back in the background here, but it's not the same type. What options does this form allow for plasma? What type of electrode is used here? And does the location of the electrode make sense, and why? So we're seeing a glow discharge, and we're seeing a little bit of a brightness happening along the points here. But we're seeing that we're mostly filling out the volume of the glass. And I think this is also red glass. Touch Me Gently by Fumi Amino. What's happening at the fallopian tubes? We're seeing an arc. We're seeing a line of bright light following through the constriction point. What do you think about the choice of gas for the light in the plasma produced? That's a question for you. I personally think it's great. I don't think it needs to go anywhere else. This is great. What type of electrode is used here? And note the location of the electrode. Does it make sense? Same thing here. What do we see happening in this form? What do we think about the choices made for the gases? And how the electrode is placed? That's design theory. We've gone through our different attributes: illumination, discharge modes, level of interactivity, electrode placement, electrode type, electrode attachment method, visibility of cords and wires, and geometry. That's a lot. That is a lot to have to go through. Um, and I try to make these faster, but sometimes it's a little bit up to students to check out what I've already put out there. But I'm really happy to be able to do this live stream, to put it out there on the internet as is, because it definitely helps. It's going to help some people. Let me see here. What else I got? Anyone have any questions they might want to ask right now? Because otherwise, I'll kind of close up. Anyone else that want to check this out can definitely come back and ask questions. I'll listen to this page and see what's up, and get back to any questions you might have. That interaction is important. It lets me know people are listening. It lets me know people are watching. It lets me know there's questions to be answered. Everything else, I have my own timeline that I'm figuring out, and I'll get to it as soon as I can. And yeah, let me go back to my page. Let's get this squared out then. So, if you want to, please support future guides and information. If you find this helpful, useful, and or educational, please consider supporting Taming Lightning on Patreon or Ko-fi. You'll be added to the page of patrons. You'll have additional monthly subscriptions between $2 and $5 tiers, early access to episodes, projects, and research, downloadable access to PowerPoints. That's Patreon, www.patreon.com/taminglightning. And sign up for the email list on Taming Lightning. That's free. Scan me. Taming Lightning subscription. Subscribe to mailing list. You get information on classes. Get information on new podcast resources, any store items I add in there. A lot of times I'll get different suggestions. I'll put them up on there. But it's a way for me to kind of communicate with you what's going on, what I'm working on, new partnerships and things of that sort. Lets me know that you're listening. So, yeah, if that's it, be safe, be healthy, and be strong, and I'll see you next time.